This is step 3, 2016, question 7. Yeah, I'm back. I haven't been uploading recently because honestly just been like busy, been traveling. Also like my results day was coming up, so I was pretty like stressed out. But it's fine, all went well. I got into my firm choice, which was mathematics at King's. So I've just been like pre-reading and just trying to like get ahead for uni. But I kind of missed doing some steps, so I thought why not. And today, yeah, we're doing step 3 because I wanted to do some complex numbers. Also, sorry about the voice. Like I'm really sick today, so it's kind of hard to speak. But yeah, okay. We have omega, which is a root of unity essentially, because e to the 2 pi I over n, and we want to show that z to the n minus 1 can be factorized into this thing here. Okay, so for something to be factorized into something, we need to find its roots. So its roots are just the root of unity, where k goes from 0 to n minus 1, right? Okay, so now that we have all the roots, we can just rewrite this polynomial as just its roots, which is exactly what they wanted us to show. So that's nice. Great. So now we have a polygon, an n-sided polygon, which is regular, which is literally just like a direct hint for us to use a root of unity thing that we just proved. Because whenever you have a regular polygon and it's centered at the origin, there's always something to do with complex numbers or like roots of unity. So it will look something like this. This is just like a hexagon because it says n is even. So I just think I'll draw a hexagon because why not? So let's just call this x0 and x1. But essentially these are all just the roots of unity. So you can even call it omega or whatever you want. But for the purposes of the question, I'm just going to call it x0 and x1. And p, which is the point equidistant between x0 and x1, is here, right? This is p. And the property of p in this circumstance is that its argument is going to be half, or like the halfway point between the argument between x0 and x1. And because x0 has an argument of 0, x1 has an argument of 2 pi over n, then the argument of p is just going to be pi over n because it's halfway between the two. So we can represent p as r e to the I pi over n. And the reason we have an r is because its modulus is it's not going to be 1, right? Because these roots of unity are on the circle, right? These vertex are on the circle. So those will have a modulus of 1. And also a property of roots of unity is that every root of unity has a modulus of 1. But P is going to have a modulus slightly less than 1, right? So, but we don't know what it is, so we're just going to call it R, and it's honestly not relevant because the modulus of P is just OP here. It's called OP. So they don't want us to find out what it is. But we do need to show that this identity holds true. So px naught is said to be the distance between p and x naught or x to whatever, and this is just equal to the modulus of p minus x naught. So we can rewrite all of this up here as kind of p minus x naught modulus times p minus x1 modulus times modulus of p minus x2 all the way up to p minus x to the n minus 1. Okay. Now p is just re to the I pi over n. So re to the I pi over n minus 1 because x naught is just 1 times re to the I pi over n minus omega because x1 is just omega, right? Like x1 is omega, x2 is omega squared. These are just roots of unity. So it'll be something like this, all the way up to whatever this thing is, the last term, which is cool. Okay, so do you see how this is like really similar to what we just proved in part one, where z pretty much just equals p, which is also equal to e to the r e to the I pi over n, and our omegas haven't changed. The only thing that's different is that we have moduluses now, but that doesn't make any difference until the end result. So we can just use our standard end result that we proved, and we know that this is going to end up going to the modulus of r e to the I pi over n to the nth power minus 1, which will be r to the n e to the I pi minus 1 modulus, and e to the I pi is just minus 1, so it will be modulus of minus r to the n minus 1. But because this is a modulus, right, and it has to be strictly positive, we multiply inside by minus 1, and this ends up going to r to the n plus 1. And r to the n, we established r was the distance from the center, which is the origin, to p, which is the modulus of p, which is OP. So OP modulus to the n plus 1, which is exactly what we need to prove, right? Now we need to give the corresponding result when n is odd, right? By the way, yeah, I should have established n is even, right? So it doesn't really change anything for this first part. But now that n is odd, there is just an extra case to consider. So the original case will still hold, right? So we don't need to prove anything new in that regard. But there is an extra case that opens up. If you draw a heptagon, I'm not going to draw it here because I don't have enough space and I don't really have enough time. But if you draw a heptagon, just look at a heptagon online. If you add pi, let's say you added pi to this point p, right? In this even circumstance, you would end up here, right? But when you have odd number of vertices, you're going to end up at another root of unity. But that root of unity is also equidistant between two adjacent points, or two adjacent roots of unity. So essentially, another place we can put p is just at a root of unity, because for an odd-sided polygon, regular polygon, any root of unity is equidistant between two other roots of unity. It's not the case here though, right? Because this point may not be equidistant between this point and this point, but for an odd-shaped polygon, that is the case. So essentially, RP doesn't need to be in between two roots of unities. It can also just be a root of unity. So what we can do, our next case, is that we just add pi to the argument. So if we tried this, right? Okay. Wait, sorry, this should be to the nth power minus 1, right? This is second case, okay? Whenever we add pi to the argument, it's just gonna turn the whole complex number negative. So it's gonna become minus re to the I pi over n to the nth power minus 1. And this will end up being minus r to the n e to the I pi minus 1. And because n is odd, this is going to continue. This is just going to be minus r to the n e to the I pi minus 1. And e to the I pi, like I said, is minus 1, right? So it's just r to the n e to the, not e, sorry. It's just going to be r to the n minus 1 mod. But r to the n is going to be less than 1, since r in itself is less than 1. Because if you think about it, if a number is between 0 and 1, since r has to be greater than 0, if a number is between 0 and 1, then essentially So yeah, for numbers between 0 and 1, if you square it or you take it to the nth power, where n is an integer, then it's going to get smaller. So r is less than 1, therefore r to the n is less than 1. And what we have to do is multiply the bracket by -1 to get 1 minus r to the n. And r to the n is once again just OP, modulus of OP to the n. So just be this. And that's our second case. That's quite I mean, if that's rushed, just put something in the comments and I'll answer it. But if you just search up a heptagon root of unity, you'll see that if you put p in between two roots of unity, like equidistant between those two roots of unity, and you add pi to that, you're just going to end up at a root of unity, and then you realize that root of unity is equidistant between two adjacent roots of unity. So it does work, but it is hard to spot. I actually had to ask ChatGPT why we did this, and then it kind of clicked to me. But yeah, okay. That is probably like the weirdest part of the question, but even if you miss that out, it probably isn't that deep because I don't think it was that many marks. Great. Okay, part two. I think part two I kind of gave an alternate solution for. It was not in the mark scheme, but I think this solution is way better if you just know L'Hopital's rule. Let me get rid of all of this stuff here. This is all not needed anymore. Okay, great. Whatever, I'm just gonna leave all this work here. Okay, I can't be asked to get rid of all of that. Nice. Okay, so now we need to show that essentially the distances of each root of unity from x naught is equal to n. And if we recall, x naught is just our first root of unity, which is just 1, right? So x naught is 1, x1 is our first root of unity, x2 is our second root of unity, and so on. So what it's saying is that x naught, x1 is just, like I said earlier, the distance between 1, the modulus of 1 minus x1, which is equal to modulus of 1 minus omega. So we're going to have the product of the distances between each root of unity and x naught. So it will be this. All the way up to 1 minus omega is the n minus 1. Okay. Now, if we look really closely, it is very, very similar to what we proved in the stem. So I'm going to write that out again. But there is a slight change because we have a z minus 1 here and we have a 1 minus omega here. So the difference is that if we plug in z equals 1, which it is, we get a 0 on both sides. We get a 0 and a 0. So what I'm going to do is I'm going to divide both sides by z minus 1. And because z is 1 here, what's going to happen is that we're going to get a 0 over 0. And whenever you have a 0 over 0 and we want to try and find a limit as z approaches something, we can use L'Hopital's rule. And if you're doing step 3, I would assume you know what L'Hopital's rule is because it is assessed. And I'm really surprised it's not in the mark scheme unless I'm doing something hugely wrong. But I doubt it because I get the right answer anyways. But what we can do is essentially just take the limit off the right hand side as z approaches 1. And once again, because it's a 0 over 0 limit, we can use L'Hopital's rule and just take the derivative of the top and the bottom with respect to z. So what you end up getting is n z to the n minus 1 over 1. And then taking the limit as z approaches 1, which equals n. And that's the end of the question. That's all of it. Yeah, I don't really have the mark scheme with me, but I remember I checked it and it said it was the least attempted question in the pure paper. But yeah, thank you for watching. I will probably try and make more videos later on. I've got one more question I want to go over, which is step 3 as well. But it is quite tough and I actually still need to finish the final part. But anyways, thank you for watching. Bye bye.